Conscious Life Expo is so happy to host Nassim. As many of you know, he's one of the leading teachers, visionary, and the most brilliant scientist that is applying his genius to prove scientifically and study and have us understand what the spiritual teachers have been telling us. We are all one. It is all connected. His amazing research, which you'll see here, he's going to be sharing a lot of his new research, really shows how we are all connected and can move forward with that light. He's also going to be sharing his movie that he's coming out with next summer. He did a crowdfunding campaign when it was one of the most successful crowdfunding campaigns for a documentary. So I'm really happy to present to you Nassim and what's going to be a wild ride of revolution and revelatory experience. And first we're going to be blessed to see his trailer of his new movie that will be coming out next summer. And so here it is.
Thank you. Thank you, everyone. It's so exciting to be here. You know, this is one of the first talk I did. Oh wow, my presentation crashed. Yeah, I haven't done a talk in a long time. It's great to be with you guys. I'm like, oh, family. Oh, Anna. And so it's exciting because I've got a lot to share, you know, that I haven't had time to be out there sharing for a while. And, you know, I'm going to try to get through it. I've got like 64 slides. And, I have some, you know, new physics I'm working on that actually is unpublished that I'm going to share today. And so I'm excited to talk about this and get your feelings on it and so on. And, you know, I think this year is just awesome, isn't it? Oh, I mean, 2015 turned over and like the day it started is like, whoa, I felt the push. And it's really kind of unfolding in this beautiful mandala, you know, this incredible changes that are occurring in all fields of expertise, and certainly in the fields of physics and scientific evolution. And, you know, what it seems to be pointing to more and more is this fundamental different view, this different approach to the world in which we start to think of the world as a connected world instead of a disconnected, mostly discombobulated, random universe. And this new view brings very fundamental philosophical and deep changes in our relationship to ourselves and the universe around us and each other. And I think that's really critical. So I titled this talk, The Connected Universe, A Fundamental Transformation of Human Awareness. And I will be talking as well a little bit about some of the papers I'm writing on consciousness relative to physics, which is a first for me in terms of collaboration with biologists and, in fact, astrophysicists. So we'll get into that a little bit. So there's a worldview change that's occurring. I don't know. We gotta ask the... Louder? Okay. There we go. Woohoo! So, it's a little bit of feedback. So this worldview change that's occurring, and I'm going to start with this. I'm going to start with the idea that, like, okay, you want to figure out the universe. Louder? You want to figure out the universe. Is that loud enough? It's a loud universe. Come forward. It's just we're getting feedback up here if we turn it up too far. Bring my mic closer. There we go. That better? No? I'm known for being loud. Especially by my staff. It's all about feedback. Yeah, it is. Uh-huh. Okay. Okay. The handheld. Is that better? Ah. Okay. So there we go. So I was, I'm going to start this talk by just like going from the basics. And if you wanted to, there's this worldview change that's occurring. And if you wanted to understand the universe, if you're trying to figure out how you got here and how it works, all this stuff all around you call reality, you would have two initial departure point possibility. One would be that we live in a disconnected universe, and the other one that we live in a connected universe. And, some of the criteria that would define these two views would be, for instance, everything emerged from some miraculous Big Bang, that like started everything. In the disconnected view, since nothing is connected to anything, the beginning has to be some kind of nothingness that all of a sudden is everythingness. And you don't really have an explanation for it. You don't have a concept on how it got there. You don't know the mechanics of it. And so right from the start, you violate fundamental laws of physics, laws of conservation of energy and momentum and conservation of information and so on, because you're making a miracle happen. So you start with a miracle. So you might as well, go to church and be told, well, God did it all, right? Because it's basically how the Big Bang Theory starts. All right. Now, in the connected universe, you have something a little different. Everything emerged from some fundamental continuous process, right? Like there's a fundamental continuous process that got everything where it's at today, right? That is not some initial miracle, but a continuous, infinite kind of process of relationship. You can, in the disconnected universe, you would have everything is random and evolution happens by chance, right? Everything, you got a big bang, everything went flying out, everything is just hitting each other randomly, and by an incredible, amazing circumstance, things just happen to hit just right so that you got here, right? But the thing is, when you do the math for that, it doesn't add up, right? Like when you do the probabilities of that incredibly amazing, chance or probability that things would have occurred just right. Because you see, any tweak of any of the fundamental forces, any tweak of anything that happened at the very beginning of this so-called Big Bang, by very, very slight changes of the fundamental forces, all of a sudden nothing comes together. Like matter doesn't coalesce, stars don't happen, galaxies don't happen, planets don't happen, nothing happens. It just goes, and it flies out. It's all done with, right? Like nothing is occurring. So, the probabilities when this the fine tuning problem, when you calculate the probabilities of that, actually working out so that it made our universe and it made us right here, right now, it's incredibly improbable that it would occur. All right. The probabilities are like 10 to the 8,800 and something. That's like 10 with like 8,000 zeros just for one simple monocellular structure to develop. Right? So it's not kind of feasible. But in a connected universe, everything is part of an information network structure producing self-organizing system. Because the thing is talking to itself. It's connected. So it knows what it's doing. It's going. It's learning as it's going. So it has feedback. It has feed forward. Right? The whole thing is talking to itself. So then it can develop super fast. Right? It can actually create really high level of complexity with very little rules, with very small information, like yes, no, like even binary. So it's a completely different view. It's a completely different result. In the disconnected universe, the universe has no meaning and no global universal coherency. It's just a big boom that happened, and we kind of got here by some fluke, and but it really has no meaning. It's not going anywhere. It doesn't know what it's doing. It's just we're kind of some bacterial life in the universe that just thinks that it's important what they're doing, but at the end of the day, it just doesn't matter because we're so small. In the connected view, the universe is a specific, I can barely see it from here. The universe is on a specific evolutionary track resulting from the collective information network of the whole. It's going somewhere. It's learning about itself. It's evolving. It's excited. It's like, it's doing one of you. It's an amazing thing. And it's looking back and it's thinking, wow, it's beautiful what I'm doing out there, you know? And it's loving itself. It has emotion. It has, you know, it has connectivity. It relates to itself. It loves itself, right? It's evolving. It's creating incredible level of complexity. And so those are very, very different views. With one simple syllable change, you know, in the view. So which one makes you feel the most warm and fuzzy? Which one would you instinctively think is most likely the correct view? You know, the connected universe, right? Which even mathematically actually agrees with what we observe, which is incredible level of complexity and evolutionary self-organizing systems. So, if it's a connected universe, how is it connected? Right? Because we hear that all the time from the spiritual masters, you know, it's all one and all this stuff. From the spiritual groups and all this, and, you know, like, you go home after a bad day at work and you're upset with your boss and you call your best spiritual friend and the first thing they tell you, it's all one, dude. Chill out, because your boss is just a reflection, you know? And so, you know, but it's like, but how is it all one? I don't feel like my boss, you know? I'm just not feeling that way right now. So, is there actually a fundamental mechanism? Is there actually physics that we can write on this stuff? Can we actually understand the physics of the universe as a connected universe, as a unified view? And where would that lead us? I mean, that if we could find that, we would come really, really close to the fundamental functions of creation. It would be very powerful. Imagine the technological developments that could come from such an understanding, for instance. The social changes that would occur if we had actual physical, mathematical, technological proof that we are completely connected to everything, not just to each other, to everything, to the animal kingdom, to the plants, to the stage, to the carpet, to everything. Like the worldview change. You know, I just went surfing in Baja because after the delegate program pilot where I had to write some 400 pages, my staff was like, okay, you're out of here. Right? I was getting grumpy. It's like, okay, you gotta take a vacation. So I was sent to Baja by force to go surf. And when I crossed the border, every time, you know, it's so shocking because you're driving along the borderline, which is a complete artificial concept, right? And you got this huge fence there. And on one side of the fence, you got these people in complete, you know, poverty and suffering in the streets, you know, with nothing, right? And you look right across the fence over there and you get $1 million homes, right? And it's like, wow, can we just take this fence off? You know? Can we just take this line we made off? Like, get everybody together and have a good time? And those Mexican dudes, they're good at having a good time. So how do we do that? Well, first of all, we would have to come up with something that connects everything. Right? We'd have to say, okay, well, what is it that connects everything? Like, if I'm looking at describing a connected universe, I would have to, find the thing that connects. And so I would have to ask the question, what is everywhere that connects every point in space? And the only answer I could come up with after a while of thinking would be space. Space is everywhere. It's in between galaxies, it's in between stars, it's in between planets, it's in between molecules or in between atoms. In the most dense molecule, like carbon, like diamond molecule, one atom relative to the other, if I grew one of the atom in that molecule so that it was an orange, the other one would be about a football field and a half or 2 football field away. That's how much space there is between the atoms in that molecule. And that's the densest molecule we have. And then if we actually looked at the atom in that molecule, we'd find, oh my God, it's 99.9999999% space. Right? So in the stuff that we call so dense, we're talking about space. Right? I get that from the spiritual community all the time. It's like, oh, it's so dense down here. Dude. We're talking about mostly space, and so there's 0.0000001% over there, and that's the thing we call matter. That's the thing we call our reality. And we're completely absorbed and concentrated on that part. Right? But in fact, we could start to think, well, maybe actually that part is just a little bit of the space that's producing a boundary. Right? Because when we look at that 0.0000001%, in fact, it's just a little electromagnetic wave that's oscillating. Right? We call it an atom. We can't, when we look at the middle of an atom, a proton, the only thing we can say about the proton is that there's a charge there. That there's a little electromagnetic charge there. That's why the radius of the proton is called the charge radius of the proton, because it's not like we're seeing a billiard ball over there. Right? It's just a little charge. So this little charge and this little charge, they're not in phase. So when I go like this, I hit something. Because, the charge are hitting each other. But nothing is actually touching. I'm sorry to say, but you have never touched anything. It's all about friction. But let's not go there. Oh. So this, so then all of a sudden you start to think maybe differently. Maybe space is the thing you should study. Maybe space is not this thing that's just empty or void of everything, but actually maybe space is the thing that makes the other thing you call things happen. Right? And so, many thinkers and some of the greatest minds on our planet, made statements that are really profound about space. For instance, John Archibald Wheeler, one of the greatest physicists, no point is more central than this, that empty space is not empty. It is the seat of the most violent physics. Right? David Bohm, space is not empty. It's full. The universe is not separate from the cosmic sea, from this cosmic sea of energy. Talking about space. Right? Einstein, physical objects are not in space, but these objects are these objects are spatially extended. Sorry, I'm very dyslexic, so you're going to have to excuse me. In this way, the concept empty space lose its meaning. This is Einstein. So, and there's many, many more quotes I could pull out from, and these are the most respected physicists on the planet, some of the greatest genius we've ever had, talking about space being the most important thing we should study, or the most important thing we should explore, and the source of most of what we experience. So why would these guys say that? Because these guys don't get to say anything if it's not written in some equation somewhere, right? They can't just start philosophizing about space. I mean, they can, but then they would get the big poo-poo from the rest of the physics community. So how did they come to those conclusions? Well, in order to understand how they came to those conclusions, we're going to have to do a little physics. I'm going to try to keep it simple, but we're going to do a little, math as well throughout this lecture. Quantum mechanics was actually discovered because Max Planck was hired to improve on light bulbs. Did you all know that? So Max Planck had this contract to improve the light bulb in the late 1800s. And he had to figure out, the thermodynamic radiation of a filament in the light bulb to try to figure out how he could make it run more efficient and last longer and put out more light and do all this stuff. And in order to do that, he had to run equations that have to do with black body radiation. That is, like the base equation to understand the radiation of an object. So imagine an object that's completely black, that absorbs all the light that's incident on it. It would heat up and radiate thermodynamically. And so those are the equations that were describing the heat emitted by objects. That was the basis for thermodynamics. And so when he started to look at this, there was a problem, is that when you ran the equations, there was an ultraviolet catastrophe, as it's called in physics. That is, when you ran the equation for a black body emitting thermodynamically, the ultraviolet part of the spectrum would go to infinity. The equation said that it would radiate infinite amount of ultraviolet radiation. And that's not what they were measuring in laboratory. So, there was a problem. And what Max Planck did, basically, is that he found that if he added in the equation this little fudge factor, and literally, he thought it was a fudge factor when he did it. He wasn't so excited about it. He thought this is kind of messy physics. And, but when he added this value, right, this little value, it all came out to what was measured in laboratory. And this value made it so that the equation was saying that actually the radiation that comes off the object is not continuous. It's not kind of like a continuous smooth curve, but it actually is coming off in little packets of energy, which eventually was called the Planck's constant, or quantas. These little packets of energy were coming off the object, and so, and it was counterintuitive at the time, because when you heat the water on the stove, it doesn't seem like it's going up in little quantas, but the quantas are so small that we don't measure them. It appears smooth. So, that was the start. And he was able to describe these quantas of energy in relationship to the energy being emitted being his constant, this little fudge factor, right? Multiply by the frequency. And so it came out just right. And eventually it was realized that this was not a fudge factor, but actually the way things are, the way the universe works, that it emits energy in little packets, which was the base of quantum theory eventually. Planck's constant defines a little packet of energy having angular momentum called a quantum of action, which eventually leads to the Bohm atom model and the electron orbit. So he was able to show that these little packets of energy, which are little packets of angular momentum, of spin, right? That these little packets of energy could be describing the way the electrons jump from one electron orbital to another, because they didn't seem to jump in a smooth fashion. They went from one orbital and then the way the universe works, that it emits energy in little packets, which was the base of quantum theory eventually. Planck's constant defines a little packet of energy having angular momentum called a quantum of action, which eventually leads to the Bohm atom model and the electron orbit. So he was able to show that these little packets of energy, which are little packets of angular momentum, of spin, right? That these little packets of energy could be describing the way the electrons jump from one electron orbital to another, because they didn't seem to jump in a smooth fashion. They went from one orbital and then you sent enough packets of energy and all of a sudden, pop, it would go to the next orbital, and pop, it would go to the next orbital. And so they were able to put these two concepts together, and they got the correct answers for the orbitals of the atoms. So this was really remarkable. It gave a fundamental theory for the structure of atoms, not just, the radiation of a black body emitter. So eventually, quantum mechanics provided a fundamental foundation for a quantized theory of matter. But there was a problem. Atoms can emit spontaneously, right? It's called spontaneous emission. So without a little packet going in, all of a sudden, it popped, from one to the other. And so they started to think there is something else going on. Quantum mechanics alone was unable to account for the behaviors such as spontaneous emission of atoms in the context of a theory where the dynamics of the atom is quantized, but the electromagnetic field is not. Meaning, like, the electromagnetic field must have had little quantities that were going in there, popping these electrons spontaneously. And that was the basis that eventually led to quantum field theory. Quantum mechanics had to be generalized to express the electromagnetic field as a quantized model of oscillation as at every point in space, leading to the development of quantum field theory, eventually expressed by Paul Dirac in 1920s. So basically, they had to expand the model not just to describe the atom as these little quantities of energy, but actually the electromagnetic field with it. And so this led to quantum field theory. But the structure of quantum field theory demanded that, like, when we actually start to quantize the field, so let me just, so quantum field theory describes space as if it was filled with interconnected discrete packets of energy and waveform, a little like balls and springs, right? So when they did that, the interaction of atoms with this lower quantum state of the electromagnetic field was what was producing the electron spontaneous emission, meaning the atoms are not just sitting in nothing. They're sitting in this basis electromagnetic field, in this fundamental field that is actually dynamically interacting with the atom. And that field is little quantas of energy everywhere. Okay? And it's everywhere. And so when they solved this, therefore the ground state of the electromagnetic field, the vacuum itself, the structure of space itself, is critical, and all calculation in quantum field theory must be made in relation to a model of the vacuum, where the vacuum itself is quantized, meaning they're trying to get to the basis of everything, and they're finding that, like, the vacuum itself, the structure of space-time itself, is made out of these little packets of energy, and it's everywhere. You guys are all following me? Okay. All right. Okay. And that's quantum field theory. And it's critical to all of the physics we write today in quantum theory. Now, so I wanted to go through this so you guys understand when I'm talking about the energy of the vacuum. This is not a Nassim, hallucination moment like that guy took too much drugs when he was young or something. This is actually in the basis of physics, and you would be surprised. It's more known now, but you would be surprised how many PhD physics students came out of universities not knowing this. Okay? Because it's not obvious the way it's taught, because it's, they just told, solve these equations, and you get this answer, and you apply it here, and da-da-da-da-da, and it's not taught in the context of the historic development of it, or the meaning of it. Because, in general, it makes the physicists, professors, uncomfortable. Why? Because when they solve for those little quantas of energy in the vacuum, the answer was infinity. Right? The amount of energy, because you had to sum up all the modes of oscillation. So imagine, you got this wavelength, and then you got this wavelength, and this wavelength. And there's no bottom to that. Right? So wait, where does this field end? Right? And the equation solves saying, well, it's infinite. Infinite amount of energy in every point. Right? Now, when that was solved, you can imagine, physicists didn't think, oh, we found God. Right? They're like, it's the other way around. They were like, oh, dude, how do we get rid of this? Right? This is no good. We gotta get rid of this infinite amount of energy in every point. Now, a person like you guys probably would have gone, oh man, this must be the source of creation or something, right? But this is almost 100 years later, we're starting to get there. Okay? It's like, oh, this field might have something to do with reality, right? Infinite amount of energy. But so in order for the mathematics to work, they had to get rid at least of the infinity, right? So they did something that's called renormalization. Now, it's not from what was called the vacuum catastrophe, right? They had the ultraviolet catastrophe and it got kind of replaced with the vacuum catastrophe. And so, they did something that's called renormalization. Renormalization is using a cutoff value. And hopefully, in this case, actually, they use something very significant. Hopefully you're using something fundamental as a cutoff value, and you just say, well, the ground state cannot go below this state. There's a fundamental wavelength that you can't get below. And so using the Planck's constant and fundamental constant like G for gravity and C for the speed of light, Planck had already outputted from his theory a fundamental unit for the universe, okay, called the Planck unit, which is the only not arbitrary unit of measurement we have, right? All other measurement units are arbitrary, but this one is not because it's based on fundamental constants. You guys following this? So the Planck unit was utilized, right? Which is a very specific length or a very specific time, if you'd like, right? So saying that the waveform of the electromagnetic field, like the photon can get smaller and smaller, but it cannot get past this length, right? Which is extremely small. 10 to the minus 33 centimeters. So that's a period with a lot of zeros, right? It's a very, very small number. Now, do I think that the universe cannot do anything smaller? Absolutely not. I think they're sub-Planckian. But from what I found, the Planck is actually a very important fundamental pixel for our universe. And we're going to see that. It's actually a voxel because it has volume. And so it's important because the universe is in harmonic relationship. You see? So the size of our universe, if our universe is pixelated, right? If the structure of space-time is pixelated across the whole universe, then the size of our universe would define how big that pixel is. Right? The whole thing would be in harmonic relationship. You guys see what I mean? And so, but how small is that pixel? Because it doesn't look pixelated, you know? I mean, but you see how smooth things look on your computer? You know? And you know it's made out of pixel. But because the pixels are small, it looks smooth. Right? How small is one of those little Planck little guy? Right? Well, let's try to get a relative relationship between size. We'll take the Vatican. They'll be my friends one of these days. And if we take the Vatican dome out there, it's pretty big, right? 42 meter diameter. Okay. And because we have incredible, dedicated people at the Resonance Project, I actually got my director of communication to climb onto the Vatican dome. And so there's Susan. Okay. And Susan is made out of about 100 trillion cells, depending on how much she ate that day and so on. And each one of those cells is made of 100 trillion atoms, right? So you guys integrate this, you know, just for a second. 100 trillion cells, that's a large number. But then imagine 100 trillion atoms making each one of those cells. And now you're kind of getting to the incredible complexity of what you are, right? So now you get as well a sense of how small an atom is, right? And so if you go in the middle of that atom, there's a little beady dot in the middle we call a proton. And in those 100 trillion cells of each of the 100 trillion atoms of each of your cells, there's one of those little protons, at least one if it's a hydrogen atom, for instance. And that little guy in the middle of the atom, right, is about the size of the head of a pin. Okay? So that's the little guy proton. Okay? He is so teeny weeny beady thing, right? You guys get a sense how small that is? Okay, that's really, 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 really small, right? Okay. What is the Planck relative to a proton? Well, if I took a grain of sand and made it a little Planck, so I grab a little grain of sand and I make it so that the Planck is the size of a grain of sand, then what would be the size of a proton? Well, there's the grain of sand, and here's, compared to the Earth, the grain of sand is really small. The Earth compared to the Sun is really small. But if I made a Planck a little grain of sand, then the proton would have a diameter of 4 trillion kilometers. Okay? Which is approximately the distance between our sun and Alpha Centauri. Okay? That's how small the little pixel is. Right? So you're not getting a sense of it just hanging out. Right? I mean, you're just not. Because people say it, but how can the vacuum be full of energy? And I wouldn't know it. But think about it this way. You're in a room full of electromagnetic fields right now that actually, have wavelengths much larger than the Planck. And you don't necessarily feel it. There's ultraviolet, there's infrared, there's radio waves, there's all this stuff. And you don't necessarily know it's there. So there's no way you're experiencing the Planck unless, you're, part of this group of psychic or, you are taking some very advanced, chemical concoctions, but this little Planck is everywhere in the space. And in fact, maybe the cause of what you call the material world when the Plancks play together. Right? So, we, from there, can calculate how much Planck there is in a centimeter cube of space. Right? You all following this? So you stack a centimeter cube of space with the little Plancks, and since they're all little vibration, they all have a little mass, right? Because E equals mc squared, energy equals mass, right? So you can calculate the mass, and the amount of mass of these little Planck in a centimeter cube of space is 10 to the 93 grams per centimeter cube, 10 with 93 zeros. That's a large number, right? Extremely large. You all notice when, in your bank account, when you add a zero, things improve rapidly. You got like 4 zeros, it's okay. You put another one, it's like, oh, that's nice. You put another one, it's like, oh, now we're getting somewhere. You put another one, it's like, oh, yeah. Now we're like, Now imagine you're like at 50 zeros and you're still adding, right? Till 94 or 93 zeros. That's a big number. How big? If I took all the stars in the universe, all the galaxy, everything we see in the observable universe, and I squished it all into a centimeter cube of space, I would have a density of 10 to the 55 grams per centimeter cube. I'd still have to add another 39 zeros to get to the density of the Planck vacuum at the quantum level. Right? It's seriously dense. right? Now we're talking about density, right? So the vacuum is seriously dense in energy. And that's why it's confusing to people, because it's like, it sounds counterintuitive. You're talking about the vacuum, but you're talking about something that's like almost infinitely dense. So it's like, but I have to use the word vacuum, because if I don't use the word vacuum, then other physicists won't know what I'm talking about. It should be called the ether, or it should be called, the plenum. It had many, many names. Many ancient civilizations talked about it. The chi, the mana, the stuff the juice that everything works with, right? That stuff has been well known and well documented for thousands of years. And it actually came out in our equations in physics almost 100 years ago. And it just went unnoticed. And this is why physics students don't get taught this so often, because it's such a huge number that in general, physicists try to avoid it. It's kind of embarrassing. Because they know they're going to have some of those bright students in the classroom going, dude, why are we pulling oil out of the ground? Right? Why do we think there's not enough for everybody? Why do we think that we have to fight for resources? I don't know who was at the panel that we just did, which was awesome. That was the best panel ever, I thought. Amazing people, amazing. And this energy is present everywhere. And in the panel, we were talking about wars and how to get into a peaceful state with each other. Well, there's a lot of important evolutionary things that have to happen in our consciousness for that to happen. But one of the most important things that come from the transformation of our awareness is that when we apply that higher level of awareness to technology, we eliminate the stressors that drives war, right? Because as long as we think that there is a limited amount of resources, we're going to continue to war for them. But when we tap into a literally unlimited source of energy, right, the whole scene changes very rapidly. Because we're talking gravitational drive, we're talking infinite amount of energy, all this stuff, the whole thing completely changes. Fundamentally. It gets much easier to be peaceful when you have access to infinite amount of resources. Right? And so, and we're going to see some of these experiments that are occurring that people don't know about in laboratories around the world that are really, really exciting. So when John Archibald Wheeler actually wrote the mathematics and talked about the vacuum, and this is why all these quotes I was quoting earlier came out from Einstein, from Wheeler, from Bohm, that the vacuum is like an incredible energy dynamic structure. When Wheeler wrote the mathematics to describe that structure, he found that it's not just nice little fluctuation thing that's going on down there, but actually that this is a very dynamic space in which not only space-time is highly energetic, but it is actually curled into wormhole structures that fluctuates all the way through the vacuum. And wormhole means that information all of a sudden can move instantaneously from one side of the vacuum to the other side of the vacuum. Right? And so this is a famous quote from him. Space-time at small enough region should not merely be bumpy, not be merely bumpy, not merely erotic, ooh, that was a Freudian slip right there. In curvature, it should fractionate in ever-changing multiple connected geometry. For the very small and the very quick, wormholes should be as much a part of the landscape as those dancing virtual particles that gives the electron a slightly altered energy and magnetism, the lamp shift. So basically he was saying these fluctuations of the vacuum are as well called virtual particles because they come up and they, alienate each other very quickly. And so they're called virtual. They're not like literally virtual. They're just very, very quick. And he's saying that this sea of energy is not just fluctuating, but it's like wormhole structures in space-time. And this is why at one point, I guess, out of a dream or something, it's a story. I have not confirmed that story, so it might be a legend. However, it is being propagated in the scientific community that one day Wheeler, in the middle of the night, figure out the electron because, there's this thing about the electron that we never know where it is or where it's going. It could be here or it could be on the other side of the universe. And this is why quantum theory is all built on probability equations because I have probably the idea of where it is, but we actually don't really know where it is. We can't actually pinpoint where anything is in complete 100% assurance that it's there. Could be on the other side of the universe. And so Wheeler woke up in the middle of the night and said, "Oh, I got it. There's only one electron, and it's going across all the atoms in the universe through these wormhole things really, really, really quick." And he phoned Feynman, like, in the middle of the night, like, "Oh, dude, I figured it out," right? There's only one electron. And Feynman told him to go back to bed. But I think Wheeler was really, really, really close. Really, really close. And so, but is this vacuum fluctuation for real? Is it really there? Did we measure it? Well, when I started giving these lectures 25 years ago, I didn't have any experimental proof that it was there. But since then, we've been able, in laboratories around the world, to be able to measure it. So we actually were able to measure it. It's called the Casimir effect. Because Casimir in 1947 figured out that if you put two plates close enough together, you should be able to eliminate enough of the vacuum from in between the plates, and the vacuum would be on the outside of the plate, so it would push the plates together, right? Because you'd create a little gradient in the vacuum. But at the time, nobody could put plates that close together or mill them that flat, because they have to be microns apart. And it wasn't until the 80s that we were able to do that. And when we put the plates together, it started to push them together, right? And it was exactly as described. And then recently, we got even more advanced Casimir effect, where instead of using plates, they're using semiconductors so that they can fluctuate the plates very, very rapidly and pump the vacuum in some ways. And the result is that we actually get photons to come out of the vacuum. Okay, so we actually are able now to extract photons out of the vacuum. Right? So it's really, really there. Okay? We're extracting light out of it. So I just wanted to show you this is not just theory. It actually has application. Okay? Imagine one day when you can walk into a room and instead of turning on the lights, you just extract photons out of the vacuum so that the room lights up. Right? That'd be cool, huh? But this is what we're talking about. This is the future of our humanity. If we're gonna make it, we're gonna make it because we finally figured out how to tap this fundamental source of energy. Now, that vacuum energy is not just at the quantum level. Now we know it's at the cosmological level as well. Right? And, everybody, how many people here have seen my DVDs? Oh, that's good. I pointed out early on in my physics conference and when I would go to give physics talks, that the current model of the universe is that it's expanding, and typically it's shown as a balloon with pennies glued to it. And when the balloon expands, the pennies move away from each other, and the pennies represent the galaxies moving away from each other. The thing is that what I ask is, who's this guy? Because, without that dude over there, nothing is happening. And, that always made the audience in the physics talks a little, uncomfortable. Because they thought I was gonna say God or something, and that would be sacrilege in the physics department. So, but when you think about it, when the balloon expands, then the lungs are contracting. So for every action, there's an opposite reaction. So there must be a source for the expansion. And that source, we know now, is the vacuum energy of the quantum world acting at the cosmological level. Right? It's called dark energy. All right? And it's, so it was first dubbed dark energy because they didn't know what it was, but eventually they came to figure out, but that's the vacuum energy that's acting at large scales. The problem is that there's a huge discrepancy between the density at the large scale, like they calculated how much vacuum energy is needed at the universal scale to make it expand, and so that density is low. It's 10 to the minus 29 grams per centimeter cube. And at the quantum level, it's 10 to the 94 grams per centimeter cube. So there's a huge discrepancy. And this is the largest current discrepancy in physics. It's thought to be the largest problem of physics currently. Right? They don't agree with each other. And I will show you how this is simply solved, in the next few slides. So our universe, now we're thinking universe, okay? We were at the quantum level, right? We're talking about this little fluctuation of energy at the quantum level. There's a lot of it. Okay? At the universal level, it turns out that if you take all of the mass we see in our universe obeys the condition of a black hole perfectly. Okay? It's really remarkable. You wouldn't expect that. But it does. Right? So this is the equation. The solution to Einstein field equation is called the Schwarzschild solution. And basically it's 2 times the gravitational constant multiplied by the mass over the speed of light square. When you make this equation with the mass that we see in the universe, right? And you calculate it, you get the exact radius of the observable universe that we can see today. Right? So our universe actually obeys the condition of a black hole. But think about it. If the vacuum energy is so incredibly dense and so incredibly dynamic, of course the universe must be a black hole. Right? With all this energy in it. But even if you forget about the vacuum energy, just the matter energy in the universe makes it a black hole. So then Elizabeth Rauscher and I wrote scaling law to see if there was a correlation like harmonics. Because think about it, like all of a sudden it's like, oh, wait a minute. The vacuum is actually just dividing in harmonics relationship and is making all the scales, right? So we wrote scaling law to see if there was a relationship between the scales, and sure enough, there was. This is the universe, and this is the Planck. So remember how small the Planck is, right? So this is a huge scale from universe to Planck, and then we plotted the stuff in between, and it fell in the right place. Okay? And both the Planck and the universe obeys the Schwarzschild condition. They both obey the condition of a black hole. So the little teeny Planck is a little teeny black hole. And the universe we're in is a very large one. And we're in between. Right? You guys starting to get a sense of where I'm going with this? 20 minutes? Oh. Okay, I'm gonna have to warp space-time here. I'm gonna need your help. Okay. So, of course, the little atom in the middle there is not thought to be a black hole in current conventional physics. So like, how is this thing lining up with all these other black holes? These are the middle of galaxies, quasars, and all this stuff, stars. And this little atom there is lining up with all that stuff. So it became clear, but the atom then must be one of those little divisions of the vacuum. But when we calculate the mass of an atom, we don't consider the mass of the vacuum inside that atom, right? So that's what I did. That was one of the papers I wrote, the Schwarzschild proton paper. I got a lot of flack for it. A lot. Okay. And basically, by saying the Schwarzschild proton was, for a technical physicist, clearly I was saying a proton is a black hole because the Schwarzschild solution is a solution to a black hole. So I was saying the black hole proton. And the proton, because I figured out it must be the nuclei of the atom that's the teeny black hole, right? And so I took the I took the volume of a proton, right? How much space there is in a proton, right? And I said, how much vacuum Planck fluctuation can be in this teeny little volume? Because the volume of a proton is 10 to the minus 29 centimeter cube. It's like super small. And so I was thinking, is there enough vacuum fluctuation to even make the proton a black hole? And when I calculated, I was blown away. Because there was 10 to the 55 grams of vacuum fluctuation inside the proton. Which just happens to be the mass of all the other protons in the universe in one proton in terms of vacuum fluctuations. Right? The mass of the universe in every proton. And there, it linked with so many ancient traditions and masters that talked about that everything is in everything, and the holographic view just emerged, right? I knew from heuristic analysis that the universe had to be somewhat fractal and holographic, but there, the math came out, right? It's like, oh! So, that was awesome, right? Like, no, it really is all one. It's not just like some concept. But you might say, well, how can all the atoms in the universe be in one? But it's just like this. Think of it that way, is that there's information in that one proton that involves all the other protons in the universe because they're all connected. Like, you can't just isolate one proton from all the other protons. You can't put a box around it. That doesn't exist. There's no box that isolates everything from gravitational field, for instance. You cannot. Right? So think of it this way. It's like a CD, right? You get a CD or a DVD, of an orchestra playing music, right? It's not like the violinist and the violin and all the people that are in the orchestra is on the CD, right? They're not on there. They're not in, but the information of the music they're making is in there, right? And it's very compactified because there, you can encode with little bits on this thing. So the bits of encoding of information in the universe is the Planck bit. And so every point in space is in contact and has the information of all the other points in space in terms of Planck bit of information. You guys follow this? So it was remarkable. And when I calculated how strong two protons that would be mini black holes like that would attract each other, I found that the attraction of those two protons would be exactly what we call the strong force. The force that holds the protons together in the nuclei of the atom, which in standard physics was just thrown in. When we found the protons, they were supposed to repel, right? Because they have the same charge. But actually it was just thrown in to make them stick together, right? And so all of a sudden I'm like, oh man, this is a classical solution to the strong force. We can get rid of that. It's actually gravity that's holding the atom together. This would be the source of gravity, actually quantum gravity, what they've been looking for. So I started to dig further. Okay. I start to dig further. I start to think, oh, maybe I got to start talking really fast. So maybe, what we're seeing when we're looking at an atom is like we're seeing the little, radiation function that's in that region of space localized, but the thing is connected to all the other protons in the universe and we don't know it. And the information transfer of all these protons with all the other protons in the universe is what actually produces the mass that we see as the mass of the proton. You see what I'm saying? And so I'm like thinking, how can I describe that in mathematics? How can I describe that in physics? It's crazy. I gotta somehow find a mathematical formulation that describes the influence of all protons in the universe on one guy. Right? And when I'm done with the calculation, it better come out with the right mass for that one guy. Like the probability of that coming out right was like kind of a long shot, to say the least. Right? You can imagine. So I'm giving you the solution, but this took me 25 years, right? Like, it's like awful. You're thinking, oh my God, this is not possible. I can't calculate that. And then the solution is so simple, it blew my mind. I was like, oh my God, how could I have missed that? Right? How could I have missed that? Never mind, how could 150 years of physicists have missed that? So what I found is this, is that actually, there was already work that was being done in the standard physics community starting to describe that the little Plancks on the surface of a black hole actually have a significant influence on the black hole. And that it is the source of its heat. And it's called the it's called the holographic principle. And I'm just going to skip slides really quick because we got to get there because I really want to show you the rest of the stuff. And the holographic principle, basically, they start to describe a bit of information as a little Planck, right? So they were kind of getting on my page, and they started to say, if we actually pixelate all the surface of the black hole, we find that 1/4 of the information of the Planck on the surface of the black hole, which is equivalent to the equator of a sphere, right, is the exact temperature of the black hole. So it came out. It's the entropy of the black hole. It's called the holographic principle, and it was accepted in physics at that point that the holographic principle was valid, right? It gives the right answer for the information that's falling into a black hole to give it its heat, right? You guys are following this somewhat? Okay? And so I said, well, that's really nice, but all these guys, they're only tiling the black hole, on two-dimensional surface. Like if the black hole was a two-dimensional, because in topology, spheres are two-dimensional. Like it's a membrane, which, there's no such thing. The universe does not do some infinitely thin membrane, right? So, and this is a problem in mathematics. We conceptualize ideas and then forget that the universe doesn't do that stuff, right? Okay? And so I said, well, the little Planck that they're tiling cannot be like Planck square, It has to be, little spheres, right? Which I call, Planck spherical units, PSUs, right? So I made a Planck a little sphere, a little spherical volume. And then I tiled a black hole, like in this case Cygnus X1, which is a well-known black hole, with all the little spheres on the surface and counted them. So I put the little spheres on the surface, and counted them. So there's 10 to the 97 little Planck sphere on Cygnus X1. That's a lot of little Plancks, And they all have, they all hold one bit of information. But I said, what about the Plancks that are inside? And it hit me. Oh, wait a minute. If the whole thing is network, right? The inside of every proton or every black hole is actually in contact with the inside of every other protons in the universe. I was starting to see the solution that I needed to get, right? I was like, can it be that simple? Can it be that simple that the information inside relative to the information on the surface defines the mass of the object? Because the information inside, there's more inside, right? Inside the volume than on the surface. So there's a restriction of how much energy can move through the system, how much information. There is a bug rate based on the surface. This is why the universe make new surfaces, like babies, so that it can encode more information, right? And so I just, I'm running out of time, huh? Dang. Okay, I gotta talk faster. Okay, so I counted how many there's Plancks inside, 10 to the 118, that's a lot of Plancks. And then I thought, maybe it's just a ratio. So then I did the ratio of the Planck outside, the Planck inside to the Planck outside to see what is the relationship. And that gave me a number, right? A dimensionless number. It doesn't have mass, right? It's just a ratio between the inside and the outside. And then I multiplied that ratio by the Planck mass, right? To get the energy of the ratio. You guys following this? And the answer was the exact mass of the black hole. The exact mass of the black hole. But in pixels, right? And so that answer is the same answer as Einstein field equation answer for that black hole. So I solved Einstein's equations just by pixelating the universe. So all of a sudden, gravity and mass is not just this smooth curve described by Einstein, but it's actually quantized, pixelated at the very, very small level. Right? So Einstein described gravity as curvature, like when you pull the plug in your bath, the surface of the water starts curving and your rubber ducky starts orbiting, right? Okay? That's what he described. But what I found is that actually the solution is actually all the molecules of water spinning, producing the curvature. The curvature is the consequence of the spinning of the little Plancks all together. So you can think of a black hole as actually the structure of the vacuum, like a slurry of these Plancks all spinning together, creating an energy event that has mass. You guys see what I mean? And so I was like, whoa, this is so cool. quantum gravity, like for real, right? And so then I thought, oh, okay, well, that's the algebraic, I'll spare you that, extrapolation of the geometry. But what was really cool is that, like, when I did the algebra of the geometry, because this is a geometric, like, straight up geometry equation, right? I realized that the geometry couldn't be that every Planck was like, was tangential to each other, right? Because that would leave a space between the Planck. The equation said there was no space between the Planck, right? So it couldn't be that. So then the space had to be taken up. And when the equation is correct for the black hole, it's because the geometry is in the shape of the flower of life. Just like your t-shirt. Which is a symbol that's found in ancient civilization all around the world, in temples all around the world, and that's described as the fundamental pattern of creation and all this stuff. I'm like, dude, these guys had it right. Not just a little bit right, like, here's the equation, bro, like, it comes out, It's not just a cool thing that you want to print on a t-shirt, And like in the Forbidden City, for instance, the guardian of the city, the guardian of the knowledge, has his paw on the knowledge. And when you look at the knowledge under the paw, there it is, right? And it's in 3D, like the proton right there, right? Well, at least the black hole. So I'm thinking, okay, pray. I mean, it took me at least 5 years of calculation to go from this step to the next step. So like, it's not like it happened overnight, but like when I found the next step, I couldn't figure out how easily I could have found that. Like I could have found it the next day, but I went through this crazy calculation, insanity for 5 years, not sleeping, literally like nights after nights, like, oh, is this geometry working? And then I finally found that if I took the proton, because like, if it was quantum gravity, it had to apply at the proton level, right? If the solution was correct, it had to be right for the proton too. So then I calculated how much were on the surface. Again, 10 to the 40th Planck are on the surface of a proton. And then how many are on the inside? 10 to the 60th. Planck on the inside. Now you're starting to feel the sense of the harmonics there, anyway. And so if you, and then I realized that all I had to do was reverse the ratio, because now as I was at the quantum level. And so now I did the surface over the volume and got a ratio, right? And multiplied it by the Planck mass, and sure enough, it gave me the mass, the proton. And I was like, oh, right? But when it gave me the mass of the proton, it was a little bit wrong. But you know what? I was really happy. Because you know what? I'm dealing with 10 to the 60th Planck inside, multiplied by 10 minus 5 grams, which is the mass of the universe. So I'm actually dividing the mass of the universe, the mass of all other protons in the universe. Really? Oh, all the other. Give me just a little more. Okay. All the other protons in the universe to the surface of the one proton, and I'm getting within 0.0012 of the mass that's measured in laboratory. Okay? Like, so, I'm dealing with mass that are 10 to the 55 grams, and I'm getting a mass that's 10 to minus 24 grams. Like, the mass of a proton is teeny, and it's coming out. Like, how, the chance of that being like some fluke is like, no way, right? This is real. And so, but then I realized, okay, I'll skip the algebra. I realized, oh, but my mass, my measurement is based on the measurement of the radius of the proton. right? Because if the radius of the proton is not exact, then my measurement, my theory may not be exact, right? So I start to look, we know the mass of the proton very exactly, but the radius is a problem. We have a hard time finding exactly what the radius of the proton is. And so I solved the equation for my theory using the Planck as a unit of measurement, right? Which is the smallest unit of measurement you could ever use, so it's going to be precise. And I made a prediction in the paper I published that radius is actually the right radius, and that they're off, right? It was a gutsy move. And in the paper I mentioned that there was this new measurement of the radius of the proton that had been taken in Switzerland by an accelerator in Switzerland that all the physicists were ignoring because it was 4% wrong to the standard model. The standard model was 4% off the measurement they took, so they were saying it must be wrong. But I put in my paper, well, in fact, that new measurement is very, very good relative to my theory. Alright? So, maybe it's right? And so, because it was within 0.00067 of the prediction I made of the proton, right? Of the proton radius. And so I published a paper with that in it, and 2 months later, an announcement was made that the accelerator in Switzerland had made a new measurement of the proton more precise than the last one. And it confirmed the 2010 measurement and with more precision, and it gave the new number, and the new number was now only 0.00036 from my prediction. And I was inside the margin of error of their experiment, so my number may still be more precise than what they can measure. And to this day, it is the most precise theoretical, prediction of the radius, the charge radius of the proton, and the mainstream is off by 4%. So, I'm doing really good on that. But, this is why you saw in many public, in popular magazine, the small, a small particle, big problem, the Hubble proton is nothing like we expected. No kidding. Because it's a black hole, by the way. And then, like, more recently, others. But I'm gonna go really fast through the slides just to get to the punchline here. Then I showed that this relationship of surface to volume ratio of information in the system is actually a fundamental ratio of the universe, and its relationship is flipping. And basically, you can think of every little Planck as the termination of a wormhole that connects another Planck on another proton, so that the thing is totally like a network wormhole structure that connects all the universe in one whole information network that is learning about itself. And mass is actually the information moving across the system. And so I calculated that interaction, and when I got it, I got the exact force that holds the proton together, but as well the range of the force that holds the protons together, which is not the same as gravity. So I was able to show that gravity, because of that wormhole interaction thing, at the atomic level, is actually giving the correct range that we measure in laboratory for the protons sticking together. And that's called the Yukawa potential. So, and when I finished this, then I calculated and this is in the paper that's coming out, that's being written with Dr. Almira Valbaker, that at the Resonance Project, that came from England to help me out with all this. But basically, when you calculate how many little Plancks there is on all the protons, you end up with that same amount of Plancks that are on the surface of the universe. So all the Plancks on the surface of all protons is the same as the number of Plancks on the surface of the universe. So the wormholes don't stop at the protons. They connect to the surface of the universe, right? So that you can, from every proton in your body, you have access to the whole thing. Like you can blow to the, you can escape our universe into the next one. I mean, literally, like the whole thing works out. It's remarkable. And so we're describing a cosmogenesis where the little proton escape our universe. One proton escaping our universe would expand. Right? Because it arrives in a larger universe, and then now the vacuum density is much lower. So it would expand very, very rapidly, and that's what we call the Big Bang. It's basically a proton, so it's biology. It's like a little seed coming out. And then, and so you can imagine universal black holes fizzing with protons emerging that like are expanding into universes. Universal cosmology, like, the whole thing is like fizzing with life, right? And so I calculated if that's plausible, and I found that it's exactly right. When you expand a proton to the size of the universe, you get exactly the density change in the vacuum. That is the difficulty, the largest difficulty they had in the density change between quantum and cosmology that I talked about earlier. And the result is that you can develop a framework of the brain, and this is what I'm publishing with the biologists now, a framework of the brain where the meningene, the surface interaction of the brain with the vacuum structure, gives you the right mathematics for molecular, atomic, and subatomic interaction with the vacuum, where the brain is acting like an antenna, connecting with the structure of the vacuum at all scales. So for instance, here's the brain cells, here's the universal structure that we can see, and here's the Planck interaction of the wormholes at the Planck level, all connecting the scales. I'm going really fast here, but I have more details for this coming up. But this is now actually being applied in technology as well. So nowadays, drives that are pushing against the vacuum, that are emerging, that have been tested in NASA. There's NASA initiatives to create warp drives using the vacuum structure. This is no longer fringe physics. This is getting more and more accepted and mainstream, and experiments are proving it. This is another experiment with superconductors that are creating gravitational fields and gravitational beams. And those have been confirmed now in laboratory and not my laboratory. So, at the Resonance Project, we are building some of these devices. And, because I was there 25 years ago, right? And so I'm a little bit ahead of the curve there. And so basically the idea is that we can take the space and engage the vacuum, engage the information in the space to create our own little slurry, right? To create our own little gravitational event, which we can control with the magnetic field, so we can lift right off this planet. We can extract massive amount of energy, and we can totally transform our world. And this is real. It's not like 10 generations from now. It's like happening right now in laboratories. And this is why, we have to keep moving. And, the delegate program is such a great thing to do, because we just launched this thing online, and you can go through all the stuff at your own rhythm and learn about it and all this stuff, and then support the Resonance Project as well. And I'm going to discuss that on Monday in this little seminar thing, and we're going to have like question and answer, and we're going to have a whole bunch of fun. So come and check it out on Monday. Thanks, you guys. Woo! Thank you. Thank you. Thank you so much. Appreciate it.